Hello everyone, my name is Yusuf Bibawi. I'm a researcher at Office e.V., Oldenburg, Germany. And today I'm gonna present the work that we done for our paper Measurement-Based Online Verification of Timing Properties in Distributed Systems. Let's start. Here is the agenda of our today's presentation. I will start with an introduction about the general idea of the paper. Then I will talk about our motivation, the challenges we try to solve or find an answer to, the methodology we followed, and the contribution we made. Then I demonstrate our contribution, and we will evaluate it in the evaluation part. Then I show the applicability of our approach in the practical application section, and finally we can conclude the work that has been done here. In this paper, we present a concept for the measurement-based online verification of timing properties in distributed systems. And we are going to provide a concept of a measurement infrastructure. So our measurement infrastructure should depend or will depend on the methodology of consistent handling real-time functions in automated systems. And the general goal of our paper was to generate timing monitors directly from timing specifications of the functions, as well as detect specified events at subsystems interfaces and to calculate signal propagation times at runtime as well. So finally, the accuracy of our concept is evaluated by a prototypical implementation of measuring instances. And our concept applicability has been proven by a demonstration including a realistic hardware in the loop simulation. And this is should be the whole structure of our paper for today. Our motivation was targeting the automotive domain, and especially due to the fact of increasing road traffic automation, maybe in the near future, it's really necessary to ensure road safety by reducing the traffic accident, of course. So that means the safety issues must be investigated during the development and the operation of the autonomous vehicles. And we will consider here one of them, which is the safe, connected, and highly automated vehicles, CHAVs. The CHAVs, in that sense, must be equipped with adequate sensors and communication systems to increase the sensing ranges. That means all the CHAVs must be communicating and send around information about the traffic situations in remote and poorly visible areas. So it can get more information than it can get by itself, by its sensors. And since now the CHAVs can communicate with each other, they can also communicate with a traffic light, for example, if this traffic light is equipped with a traffic management system. So the traffic management system can send information to all vehicles, V to X, with a V to X transceivers, so that it can support the CHAVs in crossing, for example, the intersections, by providing them information about the future signal courses. So the CHAVs, in that sense, can decide by reaching the intersection whether to cross the intersection or just wait at the traffic light, based, of course, on the information that the TMS will provide the CHAVs with. And since the interaction between the independently developed CHAVs and the traffic management system is of high importance here, and this is our concern, so it's really necessary to ensure their correct and timely functioning by development and during operation. And this is what we are going to focus on, is the interaction between the CHAVs and the traffic management systems. Since the correct and timely functioning of the distributed systems is of high importance, they must be verified at runtime by, for example, online monitoring. However, due to the systematic design methods used in designing such distributed systems like the CHAVs and the TMS, there exists a gap usually between such design methods and the online verification of real-time requirements during the system evaluation and the monitoring phase, of course. And what we thought here is we tried to close the gap between the design methods and the online verification. So it's wise and required here to make relevant timing properties that we define at the design time and make it visible during the system design in order to verify it at runtime. So the challenge here is to implement monitoring solutions for timing aspects or specifications that can be used in distributed systems. And we have identified 3 questions that we wanted to answer in this paper. First one, how can signal propagation times in distributed systems be measured and monitored at runtime? The second question is, how can the accuracy of the measurement infrastructure and individual measurements be evaluated? Third one, which accuracy can be achieved by using cost-efficient hardware and standard protocols? In order to answer question 1, we need to generate timing monitors. But the generation of the timing monitors will here depend on the results and the findings of 2 research projects, of course with industrial participation. Project 1 that we used is the multi-layer time coherency in automated driving assistance systems. That project provided us with a methodology for consistent handling of timing properties in systematic development process to ensure the correct and timely functioning of such systems. And the methodology basically was to express the system requirements into a pattern-based specification language, namely here contracts. It also provided us with a method for virtual integration tests, VIT, where the correctness of the contract's requirement can be checked in the design time. The second project was the Multic tooling, and this figure here shows how the Multic tooling can model a system. So first of all, Multic is a prototypical tool for automated execution of simulation-based VITs. And it supports the system modeling, as you can see on the right, using SysML and expressing real-time requirements in terms of timing contracts. So every component in this SysML model can be annotated with a timing contract that it must satisfy during the VIT. And the tool generates an executable System C simulation model consisting of event generators for the components as well as a monitor for every component. But the main thing is the tool generates an event generator for the assumption of the top level component and generate event generator for all the individual guarantees of the sub-components. But however, it also generates a monitor for every component, so the monitors can detect the satisfaction of the event flow during in the system. At the end, the monitoring implementation will depend on the System C coding. So System C aspects here, which are the contracts, let's say, should be encapsulated into a library called TSL-SIM, Timing Specification Language Simulator, which is used to execute the VIT and it also in the monitoring generation. The general idea behind our approach is to reuse the monitors generated for the simulation-based VIT to ensure the consistency, of course, to avoid the translation errors between the design and the realization phases, and to provide an efficient online monitoring solution. In order to integrate our monitors in the system, we need to identify the observation points, for example, the component ports in the function architecture that needs to be monitored at runtime. Then we need to map the observation points to the interfaces of the realized system. And during runtime, we can relate the events occurring at the realized event interfaces to the events referenced in the timing specification. The generated monitors from the TSL SIM library are triggered by the occurrence of events at the monitored ports. So our monitors here are event triggered components and not time triggered, they are event triggered. In order to realize the monitors, we introduce a concept for the distributed measurement infrastructure DMI that needs to observe and detect occurred events during the execution of the realized system. We call it here system under observation. The DMI consists of measuring units, and these measuring units consists of a recorder. It's used to record certain events, for example, a dedicated message from the ECU or from the SUO, system under observation, or a change of a state. Then this recorder must timestamp the recorded events and forward the information to the monitor. The monitor, in that sense, compare and verify the compliance of the recorded events timestamps with the corresponding timing specifications as according to the design requirements or system requirements. Of course, the system under observation must be designed to make the events visible to the recorder, and this is something we have to be careful during or to care about during design. Up till here, our question 1 has been answered. We know now how to generate a monitor and how can we distribute it in the system and how we can use it in a distributed system actually. In order to answer question 2, which is how can the accuracy of the measurement infrastructure and the individual measurements be evaluated? To do so, we needed to think about the technical realization of the DMI concept. And in that realization, we thought about implementing 2 measuring units, each on a Raspberry Pi. And the Raspberry Pi should exchange data wirelessly using onboard wireless chipset. And a specialized Linux kernel with precision time protocol was used on both Raspberry Pis in order to ensure the timing synchronization between the 2 local clocks of each Raspberry Pi. Of course, the Raspberry Pi needs to detect some events from the system under observation, so a GPIO based interface was selected which can recognize such events in the form of a rising edge on a previously selected hardware pin of the system under observation. Of course, to evaluate our concept as well as answering the question of which accuracy can be achieved by using cost-efficient hardware and standard protocols. The goal of our evaluation is to measure the accuracy of our prototypical DMI implementation using in 2 experiments. The first one is to measure the timing deviation between a signal generator and a single measuring unit. The second experiment is to measure the timing deviation between both measuring units when they receive the same event. The signal generator is implemented on Xilinx Z-board Zinc 7000. It can provide a square wave that contains a rising edge every selected period on a previously configured GPIO output pin, and the periods can be starting from 125 milliseconds up till 2000 milliseconds. The accuracy of the reference period was examined by using an oscilloscope that was connected to the GPIO output pin as well as to the input pins of the individual measuring units via its probes. And we wanted to make sure that the signal generator generates a correct periodic square waves with correct timing. And the figure on the right shows the correction of, or the provision of the correction of the signal generator. In order to evaluate our concept, we performed 2 experiments. The goal of experiment 1 was to evaluate the correct functioning of the recorder integration and the accuracy of the recorder itself for 1 measuring unit. The locally recorded timestamps were then used to calculate a sequence of measured periods, PM. It's calculated based on the rising age of the timestamp of the next period minus the rising age of the previous period, timestamp of the previous period. And the measured periods were compared with the actual reference period by calculating the temporal distance or the jitter based on such function here. And the observation of the maximum deviation our experiment was it has been performed for all periods as mentioned, for all the periods that has been mentioned in the previous slide. But here we show the one with 125 milliseconds. We have recorded 1000 events, and for the our observation was that the maximum deviation from the actual period for the 125 millisecond period was 10.17 microseconds, almost 8/1000%. And while for the other measurements, it was like 65.28 microseconds. So, and it shows that it's really an acceptable range. The experiment 2, or the goal of the experiment 2, was to evaluate the interaction of the two measuring units and the accuracy of the time synchronization between their individual local clocks. Both Raspberry Pis were connected to the same signal generator output pin to ensure consistency. And the accuracy of the synchronization was evaluated by calculating the jitter between the two measuring units of two boards. And based on our observation, the maximum error of 46.59 microseconds, this error was due to some delays in the detection and residual synchronization inaccuracies. And the error here can be avoided by using highly accurate synchronization protocols. The figure on our graph here shows all the deviations with different reference periods. After the evaluation of our concept, we thought about the applicability of it. So we here try to introduce a generic architecture for the interaction of chavs and other road users, and also with a traffic management system. And this architecture has been developed in the Digital Knoten project. And the heart of the overall system is an intelligent TMS that generates behavior recommendation to actively support chavs in a safe and efficient crossing of the intersection area within a strict real time. If we see the time sequence of communication on the right, the time sequence starts with a registration from an ego vehicle, and the registration should be sent to the TMS via a communication channel. Of course, this includes some latencies. Once the TMS process the registration of the ego vehicle, it should receive or asks for the traffic light status. Then it does its calculation in the process part, step 5, then provide a response to the ego vehicle at step 6, and send it to the ego vehicle via a communication channel. Of course, this step also provides some latencies. And once the ego vehicle receives the response at step 8, it needs to process it and do its action, whether to access the intersection or just wait at the traffic light. So while a successful registration at point 3 or step 3 is associated with the occurrence of a receive registration message event in the TMS, the reception of the response at step 8 is assumed to lead to the occurrence of a receive response message event in the chav implementation. So the timing requirement has been decided by the engineers that the relevant part of the communication, starting from step 3 until step 8, must follow and not to take longer than 1250 milliseconds. In that sense, the timing requirement can be represented in a pattern-based specification language as a contract, and it can be formulated as a reaction between the input event and the output event should happen within 0 and 1250 milliseconds. And this pattern shows a causal relation between both events. That means whenever the system receives a registration message, it should expect that it receives a response message within this interval. And this is how the monitor can experiment or evaluate the timing specifications as observed at runtime. So for this thing, we demonstrate this. We have a demonstration setup here, where the Scilab block here provide the information about the traffic light, the dynamics of the automated driving assistance systems, the dynamics of the ego vehicle, and the constraints of the environment. It can be communicating with the open prototyping platform for testing, simulating and measuring distributed embedded systems, Optimus, via a CAN bus here. The Optimus includes two ECUs. One represents the intersection and one represents the ego vehicle. And the third ECU represents the communication channel. Our concept was the measurement infrastructure has been presented here and connected to the Optimus. It was including two measuring units. So one recorder to receive from ECU3 the event of receive registration message. And the second measuring unit is responsible for receiving the receive response message event from ECU1. And then the measuring unit 1 should send in the information of the receive registration message event to the measuring unit 2, and the monitor, the orange monitor, now should evaluate should evaluate our specification time if it's fit to the runtime or not. And this was a hardware in the loop simulation. Of course, the two measuring units, as we developed them or implemented them, was having PTP synchronization as mentioned before. And until this point, we have answered all our contribution questions, and we successfully demonstrated. So as a conclusion, we presented a novel concept for the measurement-based online verification of timing properties in distributed systems. The DMI generic concept were prototypically realized, and we examined its accuracy into experiments and demonstrated its practical applicability. We could successfully prove that the use of our DMI enables the verification of previously specified and refined timing specifications by realized components across the system boundaries. We also showed that the monitors implemented during verification and can be reused in the system realization in order to streamline the generation process and to avoid error-prone in the re-implementations. For the future activities, we want to integrate failure avoidance strategies to mitigate the consequences of deadline misses and timeouts by calling suitable error handling methods and ensure the timely transition into a safe state. The concepts will be extended to support dynamic groups of cooperating chavs and partially virtualized TMSs as part of the follow-up project Vivre here. Thank you.